Okay. We going? We're looking good. Okay. Why have I... No, I did not mean to draw a dot. Alright. Obviously this is going to be a very good and formal video. Yeah, not exactly. Actually, I might even take my headset off for this. I'm being really informal. It's not like I have to listen to anything right now. What am I doing? I look like a nerd. Anyhow, hi. Yeah, we're doing a very, very informal video today. Also, I have my window open, so you might hear like birds and dogs and shit. Oh, I probably shouldn't swear in a video. Anyhow, I'm just gonna say I usually don't do this for recordings, but I'm just like, if I make a long recording, OneDrive, can you please like not right now? All right. If I like record like a long segment or something and I have my window closed, then like I start to suffocate in here. So, you know, not a good thing. That's what happened. I tried to record this video yesterday and it just did not go well. I was kind of like just totally losing my train of thought like halfway through. So we're doing it again today. I just like I don't know, I just kind of like did all my morning things and here we are. So anyhow, I exist and we're going to be doing a video and it's going to be on partial forwarding, which is a CPU architecture I believe I came up with. Well, according to like me and Modpunchtree. I think that's the, yeah, I haven't really talked much about this to anyone except Mod. But anyhow, I wasn't actually planning on releasing this, but well, it's just kind of, I was planning on using it in my next project, which I've been referring to as Ultima, but I think I actually came up with something better. I'm not going to go too much into detail to that because, you know, spoilers. But essentially, I don't even know if I'm going to end up using this in like this project or the next project, and I don't know. I thought it would just be interesting to share. Because I thought, like, if I don't share it now, because I mean, I came up with this like 5 months ago, and if I don't share it now, it's probably going to come out in like a few years or something, which just seems like a little bit silly. So I thought I'd just make a quick video on this. And if you guys are interested in this topic, like, I can go back and make an actual video. Like, there's going to be some proofs later on that I'm not going to like fully explain just because it would kind of take a while. But if you guys want, I can like go and make an actual video and I can explain the proofs. I don't know if that's interesting or not. But you know, it is a possibility. I've actually been wanting to try out. I've seen like voice crack. I've seen Matt Batwings use what have I done here? I'm just sitting here like I'm talking. I don't know what I'm doing. But I've seen him use like I don't know, some kind of like, oh, I remember seeing him talk about like what the program was once, but like some kind of like cool like mathy program, and I was like, I want that. So I've been wanting to like figure out what that was and like try it out. So maybe that would happen. It seems like a good time to use it. Anyhow though, so essentially, the size of these letters is just totally off. Okay, so normal CPU, you would have something like this. Also, I should have made more space here. Whatever, it's gonna be fine. And then you would have your forwarding lines, which would be, apparently I'm still very dumb today. I'm sorry, man. I'm sorry, I'm not totally functioning right now. I got up fairly recently. Yes, I understand that means my sleep schedule is terrible, but leave me alone. Anyhow, so, essentially, so wait, what? Oh yeah, it's October now. That's the thing. Anyhow, I'm getting totally distracted. Oh, it's like last time. So normally, this is kind of the setup that Modpunchtree used on the MPU-8, which I actually like a lot. But you would have something like, you would have your register banks, or you may have one if you actually have dual read registers. You'll have two if you have simulated dual read registers. And those are feeding into your ALU, and the ALU is feeding back into the register banks, and then you also have the forwarding lines, which are bypasses to the registers. Also, I should say, this is going to be a very nerdy video, so if you guys like don't know things about computers, then this is probably not going to be the video for you. So, you know, in case you hadn't picked up on that yet. But anyhow, so what partial forwarding is essentially we replace this forwarding pathway. Also, I should probably label these. We're going to call this the A side, and we're going to call this the B side. But you replace that with a, oh, that's not good. There we go. With a left shift pathway. Or at least I think it's called a left shift pathway. Okay, here's the thing. I'm pretty much like entirely self-taught, so I don't know all like the actual like computer science terms here. When you're working with Redstone, I've been working with like vertical architectures, so it's like the bits are aligned like vertically instead of like horizontally. So like if you had like a left shift or right shift is actually like an up shift and a down shift. So I think that's the right terminology. But anyhow, left shift pathway makes things bigger. Now, for those of you who aren't familiar with kind of like, you know, computers a bit, actually I just said earlier like, oh, if you're familiar with computers, I'm going back on myself. Anyhow, I just want to explain a little something, which is why this is kind of a terrible idea. So normally if you have, you know, I'm just going to go with like a 2-bit number because I can't be bothered. So if you want to left shift like a 2-bit number, then essentially, you know, you just do something like this. I was drawing fractions yesterday too, man. I don't know what's wrong with me. Anyhow, but essentially it's like all the bits are getting shifted up. But normally you wouldn't want something like this because you can actually achieve this exact same thing if you just add the number to itself. Because then it's like these two ones carry, and then you end up with, that was supposed to be an arrow, but that does not look like an arrow. That's kind of more arrowish. Is it enough of an arrow? You know what? It's good enough. It's a sad arrow. But you end up with the same kind of truth table as here. And so normally, if you wanted to or left shift the number that you just calculated, you would just activate both of the forwarding pathways and then badoom. So I understand if you've seen, you know, how computers have worked before, or at least how Minecraft computers, I don't know if actual computers differ a whole lot from this, but this is generally like a kind of frowned upon technique. But there is a reason why I'm doing this. So first of all, I want to talk about kind of what's different, like why use partial forwarding in the first place. And I think to start that off, I want to talk about the logic part of your, you know, calculations of the ALU. So the interesting thing about this, I'm not going to give a full proof right now, but essentially a number combined with any logical operation against itself, it's like the truth table for that can only either be the number itself, the inverted version of the number, or I guess, okay, essentially if you forward these, and the forwarding pathways can either output the version of the number or the inverted version of the number, or the normal version of the number or the inverted. Essentially, there's only like 4 truth tables that are possible. So it's either, hold on, so if your number is like 1, 0, 1, 0, the only possible answers, I don't know what color to do this in, we're going to do it in blue, is either going to be the number itself, the inverted version of the number, all zeros, all ones. And like I said, I don't really want to give I'm not gonna go through like every possible truth table right now. I could, if you guys want me to like revisit this subject and kind of like explain more thoroughly. But essentially, for these two, this is just you reading from the 0-bit register and then you reading the inverted version of the 0-bit register, right? These are constant. And so we can create these just fine. We don't need to do a calculation for that or anything. We can just avoid using the logic unit entirely. And the same thing actually goes for these two. So this is just the number, so obviously you don't need to make any conversions to it. And then this is just you reading the input, or the inverted version of the number. And so you could acquire the same thing by just like reading the inverted version and then routing it back and then saving it. So we can actually achieve all of the possible logical operations, and we don't actually even have to use the logic part of the ALU. And so, at least we don't have to use it for if we are trying to do the numbering as itself. And so we are actually all good on the logic side of this. So now we have to focus on the arithmetic side. Now for this, we're going to have to explain something else. So we need to consider, there's 4 different cases, but I'll explain later. It's not exactly 4 different cases, but of how we could forward the numbers into the ALU. And it's less than, it's more than. I'll get back to that. But essentially, it's you forwarding, I'm going to use a plus sign here, but the normal, just the number itself on one side and the number itself on the other side. The number itself, the inverted number, and the number itself, and then the inverted number both times. Now the interesting thing here is that since like both sides of the ALU are the same, right? Like if you have like 2 plus 1, it's equal to 3, and if you have 1 plus 2, it's also equal to 3. So since those are the same on both sides, if these two are actually like the exact same thing, right? Because it's just like the normal version of the number added to the inverted version of the number. So we can actually just ignore one of these. So in a way, it's less than 4 operations. But then we also have to consider that there's a whole nother set of these where we have to account for the carry in. I'll get back to this later, but essentially that means that there's actually like 6 different possible combinations that we can come up with, at least truth table wise. But anyhow, if we get back to here, so normal number and the normal number, that's essentially just, left shifting the number itself. So we are all good on here. The number and then the inverted number. So the interesting thing here is that if you look at this, if we use, let's say, we could use the same example, but I'm going to use a little bit of a different one. So let's say we have like 1, 1, 0, 0, and then we take the inverted version of that, and we do 0, 0, 1, 1. Okay, so let's say that we're adding these together. Now, if you look at this, this is actually just going to equal all ones, which is the same. This is the same as the inverted version of the 0-bit register. And the interesting thing here is just that essentially the number inverted means that wherever there are 1s, there are going to be 0s, and wherever there are 0s, there's going to be 1s. So you're always, the sum of these two numbers is always going to be all 1s. And so we actually, once again, this is one of those calculations where we don't even need the ALU to do this, right? Because it's just, it's always going to be the inverted version of the 0-bit register. And so we actually have this covered. And then for the inverted, essentially, it's just left shifting the inverted output of the forwarding. So we are all good on that too. Now for the carry-in, the interesting thing is that essentially, here if we examine these cases again, so we have our 2 normal, we have our normal and our inverted, and then we have our 2 inverted. So if we examine first, we're going to examine this one. So essentially, it's just the number. So if we looked at like, yeah, you know what? We can like, actually, I want to use more bits than that. We're going to do the 1, 0, 1, 0 again, but I'm going to do it over here because we have more space. So this actually, you know what? No, I should do 0, 1, 0, 1. Yeah, I like that better. So if we imagine we just upshift this really quick, then the interesting thing, so first of all, the top number gets shifted off, but then we have an interesting question of what is the bottom number, and the bottom number is always going to be, you're going to have a 0 that's shifted up, right? And the reason for this is pretty simple. It's just because essentially if you're multiplying something by 2, you don't like add in something, you know, underneath, right? It's just it's like if we have this example per se, like, yeah, this is this times like the bit, okay, every bit above, like, I'm not explaining this well. Let me words. So the bit that comes after, I'm not explaining, I don't know why I can't word this right now. So essentially bits increase by 2 times the value. So essentially this bit is 2 times the value of the previous bit. And this is kind of how things work in decimal too, except with like tens. So like each decimal place is 10 times the value of the previous decimal place. And the reason for that is just because your normal number, it has 10 different states, but binary is the same. It operates on the same kind of, it operates the same kind of way, except since you only have 2 states, essentially each value is twice the value of the previous value. And so essentially, if you upshift, then that makes, you know, that makes everything twice the value, because essentially you're taking whatever data it is and you're moving it into essentially a decimal place where the value is whatever the previous value was, but times 2. And so it doesn't make any sense to shift in an actual value here, because you'd be like adding in something additional. So essentially what carrying in would do is just adjusting this 0. Here we can just make another example. So essentially it would be, you have your normal thing, do, you upshift it, do, and all right. So essentially the only difference with the carry in is that you would have, essentially you're shifting in a 1 here. But because this is normally a 0, it's, if you're adding in a 1 here, there's never gonna be any kind of carries or anything. So you actually, like, there's no needed for any additional arithmetic to calculate this. And it's interesting too, because there's a couple different ways in which you can go about doing this. So I think it should be explained that so essentially to implement this, it's pretty simple. Either you need to add in the carry in to the left shift line too, or what you can do, if you block off, instead of blocking off the output of the ALU, if you block off the inputs to the ALU, then essentially you can just use the carry in the ALU and then combine that. Essentially, I mean, you know, if you're outputting this onto the same line, it's essentially ORing the 2 numbers. And so essentially you could just output that, and then you'll be able to, that's the same thing, because once again, you know, it's going to be, you're outputting 1 on the lowest bit, and the lowest bit has to be 0. And so there's no, you know, and so that'll be perfectly fine itself too. So either one of those methods, it doesn't really matter which one you use. But this is to say that essentially that means that, that these 2 are all good. The only one where it's not all good would be this one, because like I explained earlier, this one is actually all 1s, and so if you add in a 1 to the bottom, it's going to carry. But since this is a constant value, the number that this is going to create is always going to be the same. And if you guys know how 2's complement works, essentially this value right here is -1. And so adding 1 to -1 is going to cause a bunch of carries that's going to result in just 0. And so this is actually just a direct read of the 0-bit register. And so even though this technically would, if you were to like logic it out, it would require some arithmetic, you already know what the output's going to be because the 2 inputs are just constants. And the output is something that you just have implicitly, essentially. And so we actually have that covered too. So you're not actually really like losing any functionality here. Big stretch. I was actually looking back. I think I actually misspoken about this in my conversation of mod, but anyhow, it doesn't really matter. I wasn't looking back, but I was kind of thinking back. But anyhow, so we've talked about kind of the arithmetic and the logic part of this, but I think all I've covered so far is why partial forwarding isn't worse. And so I want to talk a little bit about why it's better. And the reason why it is better is something that I've referred to as register instancing. And this was actually one of the initial name candidates for this architecture. It was either going to be partial forwarding or register instancing. So, you know, either one of those names. But essentially, the idea behind register instancing is pretty simple. So imagine that the carry line is able to get the output of a given operation into the input of the next operation. And imagine that the register banks are one operation slower than that, right? And I should also say, just for simplicity's sake, I think this part is going to be talking a bit about control logic and stuff, so I should probably explain what type of control logic I'm considering for this. So essentially, the way I see it, there's like three different ways that you can, well, there's three different main ways that I'd say that I've kind of came across, that I've kind of came up with of you doing, activating the forwarding lines. Choice number one is that you just have the forwarding line as part of, essentially part of your instruction word. And so let's just say that you have, like, you know, okay, in actuality you would more than this, but essentially you would allocate like one bit of your instruction word, and this would just be for your forwarding. The issue here is that it is not super, well, obviously it's kind of a waste of instruction word because you have to have two of these, one for each side. So it's not the best solution, but it's definitely the easiest to implement, I'd say. Option number two is essentially change the number of registers you have. So you might have like, let's see, you might have register, and then instead of having like, right, what we have here, like 3 registers, and then the 0 register, you would have a forwarding register address, and then you would have a 0. So essentially, you could just like say like, okay, if I'm trying to read from address number 1, then I'm actually just opening up the forwarding line. I'd say this one is a bit better, but it does kind of hamper the number of registers you have, obviously. And that leads us on to the third option, and the one that I like the most, which is just essentially, you have your normal setup of registers. Here, I won't even draw this out. But essentially, what you're doing is that you're comparing the save of operation 0 let's do like double equals with yeah, computer science, with the read of the next one, or the current one. I guess this should actually be like 0 and like -1 or whatever. I guess, hold on, you know what, actually no. We're gonna do, I'm doing the word in right now. I'm doing the word in. Okay, we're gonna do, instead, this is gonna be, why, no. This is gonna be your previous, and this is gonna be your current. And so essentially, the idea here is that you're able to you're able to keep all of your registers and whatnot. It's just that if you read from the register address that is the save address of your previous calculation, then you know that that's the number that's currently in the forwarding line. So I'm just gonna, for simplicity's sake, when I'm talking about like how instructions work and whatnot, I'm going to be using, use the same blue, this one. I kind of want to do a line, and I started to do a circle. You know what? I'm going to do a circle. I like circle. There. So back to the point. Like I said, essentially, where is my mouse cursor? Okay. So this is going to get it into the next operation. It's going to get it into the operation after that. So essentially, if we imagine, if you are continuously trying to read from and saving to the same register, then this is going to be the result of your previous operation, and this is going to be the result of the operation before that. And so a really good example actually of the power of partial forwarding is the Fibonacci sequence. Because essentially, for the Fibonacci sequence, you need to have both your previous number and your previous number. Right, and then that's how you calculate the current number. Because the Fibonacci sequence is essentially adding the number you calculated before that number and the number before that number. And so this is actually incredibly compatible with register instancing, because essentially the power here is that you have essentially at a given address that you've just saved to, you end up with two instances. You have your recent instance. Oh, why is my eye so low? You have your recent instance and you have your old instance. And so essentially these two match up, because essentially, so your forwarding line is always going to have your recent instance, which is also your previous number, and then the register bank, since it's one cycle slower, is always going to have the number that you calculated before this number, or the old instance. And so essentially, you could have an operation where it's like, let's say we're going to read from like register 1 and register 1, and we're going to add these two together, and then we're going to save, or this is going to be equal to the register 1. Essentially, these two are actually two different numbers. So this one, per se, if they were assuming this is the A side and this is the B side, A side, oop, that is not an A side, B side, save. Actually, I guess this should be, hold on, we're going to do some serious computer sciencing right now. I don't know why I'm saying that today. I didn't say this in the last recording. We're gonna, also I'm doing things differently. I'm feeling big brain right now. Essentially, this is how you'd write it out if it was like, you know. Point is though, that these two are gonna have two different things. So you'll have the forwarding on this side, so forwarding, and then the B side is no forwarding, which means that the B side is going to have a slightly older number and the A side is going to have a slightly newer number, which means that the A side is going to have your recent instance and the B side is going to have your old instance. Also, these are getting a bit close. And then that's going to equate to your previous, why did I write R there? Your previous number and your previous number. I should come up with better terminology for this. But essentially, yeah, so ultimately, this means that register 1 is representing two different values at the same time, or as I would say, two different instances. And so for an example like this, essentially, we can calculate, instead of having two registers for the Fibonacci sequence, one that's representing the number you just calculated and the one representing the number before that, you could essentially store both of those values in the same register. And so that's kind of the plus side here, is essentially you don't really lose any functionality, and you're able to use your memory slightly more efficiently. The only kind of, I'd say, limiting factors to this is, first of all, it does require some, the timings are somewhat specific of how this thing needs to work. Also, I'm gonna drink water. Getting sidetracked, I'm like, ooh, water. Water is good, dude. Water is good. All right. Where was I? Oh yeah. So, like I said, the timings do have to be a bit specific, and then also the only other kind of drawback I'd say is that you do have to be a bit more particular with how you are coding it, because obviously you have to be more careful about what you're inputting on the A side and what you're inputting on the B side, because that does mean that depending on what side you're reading a number from, it could be actually two different numbers. Of course, you could resolve some of this if you make like a more advanced compiler, and so you could have something that, like, if you, yeah, essentially there are some ways around it, but ultimately I think if you implement some of those ways, it's like you could end up getting into the kind of territory of you're gonna end up really just losing some of the, well, I think it's just kind of true with abstraction that if you make something that abstracts too much, then it might like abstract away the use of register instancing, so that's obviously not good. And so I think that's probably the main drawback, you know, is that one, it's not necessarily compatible with all of yours, with every setup. You know, it's not a solve all kind of solution. And two, it's yeah, it's just a bit harder to on the I think it's called like the front end, but like, you know, to code it and whatnot. But ultimately, I feel like if you're in a situation where it's suitable to implement, there's actually, you know, like if you think that the timings are aligned such that, you know, this is useful, then, or aligned such that, I guess, like, you can utilize register instancing, it's, yeah, it's a plus. I'd say apart from that, even if you just have like a normal forwarding setup, it still, you know, doesn't lack any of the functionality. So I'd say overall, I'd consider it to be, at least function-wise, superior to your normal forwarding architecture, or functionality-wise. But yeah, I think that's probably all I have to say for the meantime. So if you guys want to see like a more kind of in-depth explanation here, I know this is already a bit long, but there are some things that, you know, I didn't fully explain, like the truth tables and whatnot. And I think that there's some things that I could explain better if I like sat down and actually made like a script for this. So I don't know if that's something you're interested in, then I can do that, but I think that's going to be all for today. So once again, just kind of an overview. Essentially, by getting rid of the B-side forwarding pathway and adding in a left shift pathway, you're able to keep all of the functionality of your CPU while potentially increasing the efficiency at what you can use your memory by having certain registers represent two different values at once. So, yeah. Peace.